Hey, welcome back to PSLE Math Lab. Today, let's solve a tricky geometry problem. Triangle ABC is a isosceles triangle where AB equals to AC. The point D and E divides AC and AB such that the D is the middle point on AC and AE over EB is equal to 2 over 3. The point of intersection of BD and CE is F. If the area of AEFD is 11 centimeters square, what is the area of triangle ABC? If you'd like to give this problem a try, pause this video now. So let's first observe and analyze the triangle and the lines given. First, we do not know the exact shape of ABC. And what I mean by that is we know it's a isosceles triangle, but the base angle is not fixed, so there are lots of possibilities. Second, we're given the area of AEFD, but this is not a regular shape. It is a quadrilateral, but it's not a square, and not a rectangle, and not a parallelogram, nor trapezoid. So we can't really use existing formulas to calculate this area. And what this indicates to us is that there must be a hidden relationship among the three sub-areas created by the lines and with the triangle ABC. So the question now is to find this hidden relationship. Since we're having difficulty with the irregular shape AEFD, why don't we try to break it up? And this is when we need some help from drawing additional auxiliary lines. We can connect either AF or DE. Both methods will break the irregular shapes into two smaller triangles. So let's start with the helping line DE. When we draw DE, we can calculate the area of ADE pretty easily, just giving the ratio relationship of D and E along the sides. But it's kind of hard to analyze nor connect DEF to other shapes because of the uncertainty where F intercepts. So we've hit a dead end. So next, why don't we try the helping line AF? Well, when we draw AF, we split the irregular shape into ADF, which since D intercepts in the middle, these two areas are the same. Same goes with area AFE. Since AE and EB has a relationship of ratio of 2 versus 3, we can calculate and relate these two areas as well. So most likely we will be able to represent the big triangle ABC in terms of these two smaller triangles. So it's worth a try. So now we can slowly start to approach this problem by examining the relationship of the different smaller areas. First, let's try to represent the areas of the two smaller triangles that we formed with our auxiliary line AF. Let's represent the area of ADF as A. And let's try to represent the area of AFE as 2B. Well, why did we use 2B instead of just 1B? Well, remember the ratio of AE to EB is 2 to 3. So it's easier for us to represent the areas of the other triangles if we use 2B instead of just 1B. Otherwise, we'll have to deal with fractions, right? So remember, we can also draw our own notations along the sides, AC and AB, to remind us of the ratios of interceptions. So this is a summary. So now we can first represent the irregular shape with the area of AEFD as 1A plus 2B, which is 11. Next, we have the area of CDF to be the same as the area of ADF, so that this is also A. Now we will have the area of ACE as 2A plus 2B. And since AE, the ratio of AE versus EB is 2 to 3, we can calculate easily also the area of CEB to be the area of ACE times 3 over 2. So this gives us 3A plus 3B. And what about the area of FEB? Well, FEB can be easily calculated to be 3B. And given the point 4 and 5, we can calculate finally the area of CFB to be the area of CEB minus the area of FEB. So this gives us 3A. Now we have all the areas of all the smaller triangles of ABC as either A or B. Continuing from our previous calculations, we know that since D is the middle point on AC, the area of ABD and CDB is the same. Just from the notations in the graph we've made from the previous calculations, we can easily write the area of ABD as A plus 2B plus 3B, which is given by A plus 5B. What about the area of CDB? Well, also from the graph, we can tell that this area is A plus 3A, which is 4A. With the above 2 points, we can have A plus 5B equals to 4A. And shifting the A around, we have 5B equals to 3A. Recall that in our first point, we have the irregular shape A plus 2B equals to 11. So now we can solve with these two equations for A. Well, we can find the lowest common multiplier of B's coefficients in order to cancel B out. So we can multiply 5 on both sides of these equations. 5A plus 10B equals to 55. And we can multiply 2 on both sides of this equation to have 10B equals to 6A. And this we can cancel out 10B altogether to have 11A equals to 55, which gives us A equals to 5. And that will basically give us the answer because the area of ABC is equal to 2 times the area of CDB, which is equal to 8. A, which is equal to 40. Well, looking back, we can really appreciate the importance of adding the right helping line or auxiliary line and understanding how a single helping line, in this case AF, can turn a seemingly impossible question into an easy one. Like and subscribe if you find this question interesting and you've learned something new. And don't forget to subscribe and turn on the notification to keep up with our latest videos. Thanks for learning with us and happy June holiday. See you next time.